You all right? Okay. Yeah, I know it's the last day, but I still don't like sleeping in my class. So, well, I would like to sleep in my class, but I don't like it if you're sleeping in my class. Half the time, I am sleeping up here and just like robotic talking. So where do we start Cal 1? Anyone remember what the whole class started with? Well, I mean, the first calculus topic, limits, right? From the idea of the limit came the idea of the derivative, right? And the derivative basically gave us the slope of the tangent line, right? And if we look at the derivative in terms of distance versus time, then the derivative was the instantaneous what? Instant velocity or speed. Okay? So if you tell me where something is at every point in time, I can tell you how fast it's going at every point in time, right? Anybody remember what the second derivative represented? Your instantaneous acceleration. Okay, so we had the idea of the derivative. Then we did implicit differentiation. When did we use implicit differentiation? Anyone recall? There's two variables, and we couldn't solve for one of them. Like something like this. Sine x plus y equals y squared x. And we were trying to find y prime, right? You can't get y by itself on one side of the equation, so you couldn't do a traditional derivative. So we introduced what's called implicit differentiation, right? And then we did, from that, related rates. Those are the word problems, right? A sphere is growing so that its volume is always increasing at a rate of blah, 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 blah. How fast is its diameter increasing when its volume is blah, blah, blah? So related rates, word problems. Then we got into, pretty much after that, we got into like graphs and then being able to do like max-min stuff. And then optimization. So if you look at this kind of as chunks, the limit and the derivative kind of went together, right? The limit is kind of the womb, right? And the derivative is the offspring of the limit. I like that analogy, right? You like that analogy? The limit birthed the derivative for us. So they are intimately connected to each other. And then we talk about velocity and acceleration from that. Then implicit differentiation gave us ways of differentiating equations that involved variables we couldn't solve for. And from that, we also could do related rates. Things like, what's the derivative of 1/3 pi r squared h? Something like that, right? We could say dv dt equals 1/3 pi, 2 dr dt. You remember all that stuff? I mean, so that required implicit differentiation. And then the graphs, finding max and mins, allowed us to do optimization. Like the problem we just did, the Norman window. So those are kind of like three basic chunks of Cal 1, right? Calculus 2 is a different ballgame, okay? Calculus 2 starts basically with the concept of the antiderivative. The antiderivative. And from that, okay, so that's the womb in Cal 2, is the antiderivative. From that, you have all these different things that come off of it, all right? The first thing is that if you're given acceleration versus time. You can recover from it velocity and position. So it's kind of like in Cal 1, if we were given the position of an object at every point in time, we could tell you the speed and the acceleration at every point in time, right? In Cal 2, we can actually go backwards. You start with the acceleration, you can go back to the speed and to the position. So anti meaning backwards, really. And then also, we get from the antiderivative this concept of area. And this is one of the huge things in Cal 2. What we do is we look at a graph, bless you, and we cut the graph off at 2 points. And we ask ourselves, what's the area underneath this? And it turns out that the area is connected to the antiderivative. So in Cal 2, you're able to find the area of very complicated shapes that don't have rectangles in them, right? Everyone can find the area of a rectangle, but find the area of that. It's hard to do, but Cal 2 you can. That kind of makes sense? And then you do something like this in Cal 2. You say, instead of looking at a single function, let's look at two functions like this. I'll do this one in black. Like that. So those are two polynomials. And they intersect each other at those 2 points, right? What's the area in between those two functions? Right? That seems like a reasonable question. You could look at that, where would this be applicable? I don't know, like taking a cross-section of, that bottom one looks kind of, not like a real wing for an airplane, but, think about a cross-section of a wing of an airplane, right? Something like this. What's the area of a cross-section of the wing of an airplane? You could figure that out using Cal 2. All right? Then you start to do some weird stuff in Cal 2. You do things like take this picture right here and imagine taking that and taking that picture that's on a piece of paper, bringing it out into three-dimensional space and just rotating it around the x-axis. So take that red thing in A right there with the question mark and flip it around the x-axis. If you flip it around the x-axis, you get something like this. Right, something like that, and there would be a solid. And what do you think the question in Cal 2 will be? What's the volume of that solid? Right? So you could take some pretty complicated looking things and find volumes of them. What would happen if I took that second one and wrapped it around the x-axis? You would get something like that again, right? What would the difference be, though? It's hollow inside, right? You would have something like this, but inside, both ends like that. You could put your finger through the middle of it, couldn't you? So it would obviously have a different volume than the one above it. Right? And hey, what stops us from rotating it? Why do we have to spin it around the x-axis? Why don't we go around the y-axis? So what would that top one look like wrapped around the y-axis? Wouldn't it be something like this? It's difficult to draw these right now for you. But if you wrap that top one around the y-axis, wouldn't you be able to put your finger through the middle of it? Isn't the volume of the two different completely? It's a completely different shape, isn't it? So these things that you do, these are called solids of revolution. And then you do something else in Cal 2. You take a function like this again, but instead of talking about areas, imagine taking that taking that graph, right? Taking those 2 points off the piece of paper, looking at it as a piece of string, and straightening it out and measuring how long it is. Right? Like if this were a rope, take it off the page, straighten it out, measure it. How long is it? That's called arc length. So you can do that in Cal 2. You can also revolve this around the x-axis and not only find the volume, you can find the surface area, which means if you were trying to paint the outside of it, you would know the area of that surface. All right? That's just the beginning of what Cal 2 is about. And then you get into sequences and series and polar coordinates and all these different things. But I want you to just see the beginning here, okay, of Cal 2, because that's what I want to talk about for the remainder of what I intend on doing today before we talk about the final. And that's to introduce you to the antiderivative. This is what some of the things you can do with it, all right? But what is it? What's the antiderivative? So here we go. Antiderivatives. This will be on the final. Capital F of x is called, I'm sorry? I'm not even going to label this as a section because I'm basically just teaching out of my head right now. I'm not teaching out of the book. This is just antiderivatives, what it's all about, kind of, okay? Capital F of x is called an antiderivative of little f of x if the following is true. The derivative of capital F of x equals little f of x. That's it. That's what an antiderivative is. It sounds simple, right? So let me give you some examples, all right? Example. Would you agree that capital F of x equals x to the fourth, x to the fourth is an antiderivative of little f of x equals 3x to the, 4x cubed. Is that true? Yes? Because according to this, to be an antiderivative means that if I take the derivative of this, right? Take the derivative of that. What is the derivative of that? 4x cubed. That is the other function over here, right? Well, what about this then? Capital F of x equals x to the fourth plus 2. Is that an antiderivative of this? It is also, isn't it? Because when I take derivative of x to the fourth plus 2, derivative of 2 is 0, and that still gives me 4x cubed. In fact, I can take x to the fourth minus 100 pi to the 70th power, right? 100 pi to the 70th power is a constant. When I take the derivative of that, I get 4x cubed. Right? So how many possible antiderivatives are there? Infinite. So there's an infinite number of antiderivatives, but they all look the same. They all have to look like what? All of them would have to look like capital F of x equals x to the fourth and a constant. Good. Plus some constant. It can't vary from that though, right?